Problem set number 7 for derivative reviews. If you're already to this point, you are kicking ass. Okay, let's take some derivatives. The first one in this group is y equals sine of x to the 1/2 to the 1/2. Like that. Now see how much better that is than writing it with square roots that are confusing? Well, it becomes obvious now that the outside function is what we're going to be taking derivative with, right? So y prime is just going to equal 1/2 sine of, or 1/2 original input sine of x to the 1/2 to the negative 1/2. Now we're going to do some derivative times, chain rule, derivative of the inside, cosine of x to the 1/2 times chain rule, well, do it from in here, derivative of the inside even farther, 1/2 x to the negative 1/2. So what does this become? I think this is going to get kind of ugly, isn't it? So we're going to get 1 over 2 root sine of root x times cosine of root x times 1 over 2 root x, I think, like that. So if I condense this, you're going to get cosine root x on top, and you're going to get 4 root x root sine of root x. Now, can you combine the roots? I'll let you decide whether or not. This is the answer here. So the first one's not too bad. Problem number 2, a little tougher than it looks. It's so condensed, you'd think, oh, no big deal, but we have an x in the exponent. X's don't belong in exponents. How do we get rid of x from exponents? Well, we take the natural log of everything, if we can. So you get ln of y. And remember, the whole point of natural log is that it lets you bring this out. So you're going to say equals the ln, x ln cosine of x, like that. Make sure you can do this. Are you able to do this? Are you able to bring that x out of the natural log like that? Do you remember how to do that? We've got explainers, we've got derivative practice, and I think we even did it in a couple of the earlier review sets here. If you're doing a final in calc, you better be able to bring the x out of the exponent. Okay, I'm coming off my high horse. Now I'm going to get on my low horse. Let's do a ddx here, like this. So what's the derivative with respect to x of the natural log of y? You're still going to take the derivative. Natural log is 1 over y, 1 over the input, but you have to chain rule dy dx onto it. And that's going to equal, this is going to be a product rule. It's x and a function of x over here. So u prime v plus v prime u. The derivative of x is 1. V is just this ugliness, natural log of cosine of x, like that, plus v prime, which is 1 over cosine of x, chain rule, times negative sine of x, right? The inside is not just an x, so you have to chain rule. That's v prime, and then u is x. So what does this look like when we clean it up? We have the same on the left side for now. Natural log of cosine of x plus, well, it looks like it's going to be a minus, x tangent of x, sine over cosine, yeah? And then this, we can multiply up, we can multiply the y up here, so we can do like this, and we'll say this is what our dy dx is going to be. And what's y? We can get rid of y because we can write in what y is. Just wipe that mark right off. Y is cosine of x to the x. I don't know if it's going to get simpler than this. I think that we're going to leave it like this as the answer. I don't know that it's going to get any nicer than this. So that's problem number 2. Let's see. Now let's move on to number 3. I do not like the way number 3 looks, but I think I have a trick for you. See this ugliness? You see this ugliness? I'm going to show you something cool. Let's take the natural log of this. And I could write it as ln of this whole thing, like that, like this. In fact, let's back up even more. I can write it as 4 ln x squared plus 1 minus 3 ln 2x plus 1 minus 5 ln 3x minus 1. Now we don't have to do a quotient rule. How dope is that? Well, we'll see if once we take the derivative, maybe I'll end up doing it anyway. But I'm going to give this a try because quotient ruling this or like foiling that out, what a nightmare. That'd get ugly. So I'm going to try it this way. Let's take the derivative. 1 over y dy dx equals 4 over x squared plus 1 times 2x minus 3 over 2x plus 1 times 2, chain rule, right, derivative of the inside since it's not just an x in there, minus 5 over 3x minus 1 times, what's the chain rule? 3. Okay, so what do we see here? We see 8x over x squared plus 1 minus 6 over 2x plus 1 minus 15 over 3x minus 1. Thank you, natural logs. And now all I have to do is multiply each side by y to make that go away. So that would be times the original. Which takes me longer to write than it took me to write the derivative. Just like that. This is the answer. How cool is that? That was only a couple of steps. This, the ugliest one in the group, only a couple of steps. And yeah, it's kind of big, but it actually wasn't a lot of work. I think that's so neat. Well, that's number 3. Okay, I love equations with e to the things in them, because they always turn out to be cool. And they usually show up all over in life, which makes them cool. That's an ugly e, though. That's closer. So y prime, this should be pretty straightforward, because the derivative of e to the x is e to the x. So we'll write e to the cosine of x like that. But then chain rule. So it's going to be times negative sine of x. Just the derivative of the exponent there, wouldn't it? And then we can treat them separately because they're just separated by simple addition. We don't need to, they don't pay attention to each other at all. So the derivative of cosine is negative sine of e to the x. Now the question is, do you chain rule this? Well, the answer is of course you do. Because it's not just an x on the inside. And if it's not an x, it's an e to the x, then you got to take a chain rule. And the derivative of e to the x is e to the x. So is there an easy way to break this up? I don't really see it. I think I would just write this as negative sine of x, e to the cosine of x, plus, well, we do it as minus e to the x, sine of e to the x, like that. That'll be our answer. That one's pretty easy. What about the 5th one there? I don't know about the 5th one. Let's have a look. And for the last one in this problem set, this group's been a lot easier than the last few. I think section number 6 was kind of hard. This tan pi theta thing, I don't like that much. Maybe I spoke too soon. Let's see what we're going to do here. Well, where is my function. Think instead of x, they're using theta, which means it's in the exponent. What do we do with the function in the exponent? It's the same thing we do every time, right? Every time. What is it? I'm going to take a natural log, the whole thing. They'll say ln of y equals tangent pi theta ln of 10. And now that's just a number. That's just a number. It's a constant. It can come right out of the derivative, which we're going to take now. We'll take the derivative of this whole thing. So we're going to get 1 over y, dy, I should say d theta, not dx, d theta. This dark spot is a theta. And that's going to equal, we can take the ln 10 right out because it's just a number. And now what's the derivative of tangent? Do you remember the derivative of tangent? I want to say it's secant squared. Isn't it secant squared? You're going to have to check your notes because I don't want to derive it for this problem set. We've done it a bunch of times. We'll say it's secant squared, pi theta, times the derivative of the inside, just pi. Okay, now what are we missing? Well, we got to bring the y up. So multiply the y up to here. So we're going to get dy d theta equals ln 10 pi secant squared pi theta times tangent, well, we'll just say times 10 to the tangent of pi theta. Can I combine any of this? Not really. This is our answer. This has been an entire set of easy problems thanks to the properties of natural logs. I hope you're paying attention to that because it is a big deal in calculus. A big deal. I'll see you in problem set number 8 on this differentiation review. Pyah!